We start a new section on estimation and regularization. Estimation has to do with estimation of the parameters of the model. So this is basically a process of calculating values of model parameters. And we say estimation rather than calculation is because we are trying to highlight the fact that the values of those parameters that comes out from this process are not the true values, but rather than estimated values, and the estimation depends on the data set. And if we move from one data set or from one sample from a population to another sample from the same population, then estimated values can be different. And they always will be centered at around the true value, which we don't really know. And the regularization is the process of estimating a simple model or trying to derive a model which has smaller number of parameters. So this is process of deriving a simple model. And we actually did do both of those things, estimation and regularization, before. If you remember, when we tried to estimate the parameters of a normal distribution, so let's see how we did estimation before. You remember example of a normal distribution when we assume that our random variable follows normal distribution, which has two parameters, mean mu and variance sigma squared. And we try to estimate the values of mu and sigma squared from the sample. So we have sample, our observed data set, we have n observations in the sample, and then we said that simply the estimated value of mu is just the average across those observations. And the estimated value of the variance is just the average of squared deviations from observations to the average. And we use those hats again to highlight the fact that those are estimates, those are not the true values. If you give me a different sample, I'll recalculate those values and I'll get slightly different mu hat and sigma squared hat. But central limit theorem allows us to say something about distributions of those averages from one sample to another. You remember, if you take another mu hat, then we should have mu hat follow normal distribution, which is centered at this mu hat. Again, we have an abuse of the notations here, so we use mu hat on the left-hand side, on the right-hand side. Actually, you know what, let's not abuse the notation. Let's use x bar, and sigma squared bar divided by n is this. So CLT tells us that the true mu hat, or mu hat that comes from a potential different sample, is just normally distributed, centered at x bar, which is our best guess about what would be the center of this distribution. So that's how we did estimation before. We just calculated the averages. And another example of estimation, you remember when we talked about the normal model, linear model. When we had linear model y equals beta 0 plus beta 1x plus epsilon, then we were able to write analytical formulas for the beta 0 and beta 1. So we were able to calculate them from standard deviation of x, standard deviation of y, and the correlation between x and y, and also we needed to know x bar and y bar. So once we calculate all those quantities, there were formulas, we can plug them in here to do and calculate beta 0 and beta 1. So you saw a couple of examples of the estimation. And when we talked about finding simpler models, let's talk about, let's review this. When we talked about model selection, and usually the goal of the model selection is to find simplest but adequate model, but useful, simplest but useful model. So model has to be simple but not too simple. So the principle is model has to be as simple as possible while staying useful. And in machine learning, they call it Occam's razor, this principle. Occam's razor. All right. And you remember when we did this model selection, when we tried to simplify the model, we used this p-value selection. We eliminated predictors based on p-values. Okay, so that's the principle we've used before. Now, in this section, we're going to learn another principle that would allow us to eliminate those predictors in a more automated fashion and a more disciplined way, and we're going to do it through regularization. So in this section, we're going to do regularization to achieve the same thing. But let's start with estimation. We will use principle of maximum likelihood to perform the estimation. And this is how we're going to estimate the parameters of the model. And as I mentioned previously, we did, from the normal, we did calculate average from the sample and then square deviations to estimate the parameters of the normal. And for linear models, we use the least squares principle. And in a simple linear model case, when you only have beta 0 and beta 1 parameters, we were able to analytically calculate them using correlation averages and standard deviations calculated from the sample. And maximum likelihood is just more general approach that generalizes previously used ways to calculate parameters of the model. And the parameters that come out from this approach, maximum likelihood, is called maximum likelihood estimates, or MLE, meaning that those estimated values of the parameters were obtained using this principle of maximum likelihood. This is something we talked about, so that's how we did things before. And in MLE approach, the principle is the following. We calculate estimated values by maximizing the likelihood function. And the likelihood function is nothing but the value of a joint probability of the observations. So you have for each of the observations, and usually what you have some probabilistic model, meaning that you have probability of observing xi given the parameters of the model. And let's say xi follows normal distribution with mu and sigma squared as mean and the variance, and then you will know what's the probability of observing xi given mu and sigma squared, and this value is actually given by the density function of the normal distribution. So you have this normalizing parameter 1 2 pi sigma squared square root, and then you have exponenta, and here in the exponenta you have minus 1/2 xi minus mu divided by sigma, and you have square here. Okay, so you have some density function, so you know the likelihood of observing each of those samples. And then if samples are independent, if xi is independent of xj when I not equal to j, meaning that if you take any pair of observations that are independent of each other, then the likelihood of observing the entire sample, likelihood of observing x1, x2, all the way to xn, so the likelihood of observing the entire data set is just the product of individual likelihoods. Probability of x1, likelihood of x2, all the way to xn. So this independence gives us the convenient way to calculate the likelihood. Likelihood just becomes the product of individual likelihoods associated with each of those samples. And in maximum likelihood case, in general, our model has parameter vector theta. And in case of normal model, the parameter vector theta just going to have two elements in it, mu and sigma. If you have Laplace, if you have Poisson distribution, then theta is just a single number, lambda. And if you have binomial, then your theta is just going to be a single value p. Okay, but let's go back to the case of normal distribution. We're going to use this principle of maximum likelihood, meaning that given the likelihood, we'll try to find the value of the parameters or estimate theta hat, which maximizes. Actually, here that should be maximized. That's the typo here. So we try to maximize the likelihood. So we try to find the value of the parameter which makes the likelihood of observing the specific sample as high as possible, meaning the parameters that we find give us the most probable explanation of the observed data set. And let's go back to the example of the normal distribution. So again, the density function for the normal distribution is just exponential function. Here we have xi minus mu divided by sigma squared, and we have this normalizing constant here. And the likelihood or joint density, assuming that samples of xi are independent, is just the product of those individual likelihoods for each of those samples. We have n samples, each individual sample has this likelihood, and we take the product of them to get the joint likelihood or the joint density function for the entire data set. And again, we write it as a function of mu and sigma squared because each of those p of xi will have this mu and sigma under it. We don't explicitly write it. Actually, we explicitly write here mu and sigma squared. And so that's the likelihood is just a product, and that's the function we'll try to maximize. Now, if we try to maximize this likelihood function, if we try to find the maximum of it with respect to mu and sigma squared, we have to use the solver, optimization solver. However, this function is non-concave, which means that we have to deal with nonlinear optimization problem, which is very hard to solve. Fortunately, there is a way to avoid solving this hard optimization problem by converting it to a simple optimization problem by taking the log transform. If we apply the log to this function, we're going to get log likelihood. And instead of optimizing the original likelihood, we'll optimize the logarithm of the likelihood. And fortunately, the solution of the problem doesn't change because logarithm is monotonically increasing function. So if you apply monotonically increasing function to your objective function, then it doesn't change the solution. However, applying the log, the function becomes much easier to optimize. My function actually becomes concave. And then there are very efficient numerical algorithms that allow you to solve optimization problems when objective function is concave. Let's write down the log likelihood for the normal distribution. So we have logarithm of the product, and here we have individual densities for each of the observations, function of mu and sigma. And you remember the log of the product is sum of the logarithms. So if we expand this big product, we get a sum. And if you look at this carefully, so now we want to look at this as a function of mu and sigma, or sigma squared. What you see here is that as a function of mu, we have negative, and then we have a quadratic here, so it's actual concave function. It's upside down parabola, negative squared. And with respect to sigma squared, you have 1 over sigma squared and the log of the sigma. So we also have two concave functions here with respect to sigma. So we have concave function with respect to sigma and with respect to mu. And if you remember your high school calculus, if you try to find the maximum of a concave function, it's basically a critical point where derivatives are 0. So we just find the derivatives of this function. The first derivative with respect to mu is nothing but the deviations between xi and mu, and adjusted by 1 over sigma squared. And if you set this one to 0 and you try to calculate what's the value of mu that leads this to be 0, you actually will find out that the mu hat, the optimal value, is just x bar, which is nothing but the average across all the observations. And let's do the same and take the derivative with respect to sigma. So you have 1 over sigma plus sigma to the negative, to power negative 3, and then some xi minus mu's. And again, if you set this one to 0 and you try to find the value of sigma squared that leads one to 0, then you get this value, xi minus x bar squared. So you actually see that the results that we get here is the same as our moment-based estimation when we try to estimate mean and standard deviation by just taking the average of the sample and calculating deviations from this average and observations in the sample. So this general principle of maximum likelihood estimation leads to the same results that we obtained basically intuitively by taking those averages before. Okay, so and let's look how it works in general. So in general, we have some model. We have a conditional distribution of y given x, and this distribution parameterized by some parameter beta, and so prediction y is random, and we use the model to calculate the expectation of y given x, and usually it's some function applied to this x transpose beta. So in case of the linear model, the function f is just identity function. Identity means function that doesn't do anything, transforms x to x. And in case of classification, f is logistic function, right? Okay, and then we're going to talk about a couple of things. We're going to talk about deviance. Deviance is the distance between fitted values and measurements. And you remember in the linear model case, deviance, in the linear model case, we used the principle of least squares, and we tried to minimize the distance between predicted observations y hat minus observed ones, and we squared those, so those are residuals squared, and then we sum up those residuals and we try to minimize that. So essentially, this value here, those residual squared, sum of residual squared is the deviance. So that's the distance between the fitted values y hats and the y itself, the observed values, and then we have the square, so we avoid this cancellation of negatives and positives. So that was principle of least squares for the linear models. And the likelihood, the principle we just talked about, that's the probability of a data given parameters. And the goal is to maximize, which leads to the maximum likelihood estimation. So those two principles, you saw the application of those applied to linear models. Okay. So again, the deviance is just the distance between the actual observations yi minus the predictions, so beta transpose xi, and then you can take an absolute value of those differences, or you can take squares, or in general you can raise it to any power p. So when p equals to 1, you have mean absolute error. When p equals to 2, you have mean squared error, the one we talked about before. And the likelihood is just the product of individual densities function calculated at the observed points. Okay, but they are connected. They're connected. The deviance is just proportional to the negative log likelihood. So essentially, maximizing the log likelihood, is the same as minimizing deviance. Okay.